Annyce, and this is
Adeyemi.
And today we're going to take you on a journey through the application that we created in order to support offline use inside of our application. But first I want to give you just a little bit of context about it. At Off Grid Electric, our goal is to provide solar energy to homes in rural Africa. And we're really dedicated to improving not only the lives of our customers, but the lives of our workforce as well. That's why it was so important to us to be able to provide them with an application that worked extremely well whenever they were offline. Today, we're going to look at the following 3 areas. First, the challenges that we faced in trying to develop this particular application. We're going to walk you through the resulting architecture that we landed on in order to deal with many of those challenges. And then finally, we're going to look at the third-party libraries that we used in order to achieve our goals. So as I mentioned, we're going to start off with the challenges. And throughout this presentation, you'll get to enjoy several gorgeous pictures from my trip to Tanzania. So that's what you see here. This was a monkey kind of hiding from us when we were on a safari, which was like pretty cool, actually. So our users work in network poor areas. And in this picture, you see a group of our sales officers all kind of huddled around trying to find a 2G connection. So they're going through each phone, trying to see if they can get it to connect to 2G in order to complete one of their orders. For us here in the States, we often assumed that our users would always have access to Wi-Fi, like at least once a day. That wasn't the case. Then we assumed, hey, they'll probably always have location services on. That also wasn't the case. So these were some of the challenges that we had to be aware of and really think about in the design of our application. Also, when our users did have network, it was extremely slow. Like, we really had no idea how slow the type of network connection that they were working with. And just to give you a little bit of background on this, in this diagram, this shows 3G coverage in one of our major countries, Tanzania, and the little white marks there, we can point a little bit, are the cell towers that have 3G coverage. So that little bit of gray area is kind of like tower, teeny bit of coverage. And then this is only in the major cities inside of Tanzania. Just to give you some more context, this is 4G LTE coverage in our nation's capital, Washington, D.C. It's basically everywhere. And we still complain about having slow network speeds. But this is the type of thing we were trying to be aware of in order to really push ourselves to be more conscious of how we were interacting with the network and when. So from these various issues, we learned 2 main things. First, don't assume anything. We started to try to emulate the network conditions for all the various flows, and we often just tested the app in airplane mode to make sure we were never blocking our users. Second, be resilient. We wanted to design the app in such a way that no matter what the network condition was, our users would never be blocked and they would be able to continue to do their work. So in order to start reviewing this architecture that we designed, I'm going to turn things over to Moyin.
Thanks, Annyce. So very quickly, I'm going to take us through the overall architecture of our application and our goals. So our main goal was to be useful to our users regardless of our network conditions. I'm sure you've all used applications with endless spinning progress indicators when you are offline, and we know that that's not the best experience. Yet our goal was to allow our users to interact with our app and still perform action regardless of their conditions. So we stuck with the following tenets. We aim to store data locally, we aim to separate the UI and network, and we aim to queue requests. In order to achieve this, we used the MVP pattern when architecting our application, as this allowed us to decouple components and have several components more easily. So how did we do this in practice? We had the typical view, which consists of activities or fragments. We had the presenters, which contain the business logic and handles interactions with the views. We had the service layer, which allowed us to to interact with multiple data sources. We had the repository layer, which abstracted away the underlying implementation, all the queries from the service layer, and then we had the database to hold our data. We also used the job queuing system, and this allowed us to schedule jobs. So irrespective of the network condition, the users could still perform actions. And then we used Event Bus and RxJava. We used that to propagate state changes. But first things first, on first load of the app, when the user first installs our app, we made sure to download all the data they would need. This includes all the key pieces of information that they will need to do their jobs. And before we display a view to the user, we ask ourselves if the view needs pre-populated data. If so, we will then go through a certain flow. So we'll start with our activities or fragments, sending a request to the presenter to retrieve the needed data. And then the presenter would ask the service, and the service would look to the repository. The repository would then perform the required queries and then get the data from the database. And this will be propagated back up the chain until we get to the service layer. At this point, we have our event bus that notifies the subscribed presenters, and then those ones retrieve the data and send it back to the views, which then perform actions based on that data. We also, when the user wants to take an action, we also ask ourselves if the network is available so that we don't display the progress indicators. And if it's not, we use a very similar chain of flow to the one we previously had to display a view. And what we'll do in this case is we'll send the data from the view to the presenter, to the service layer, to the repository, and then we'll store the modified model in the database. And then we would schedule a job to sync this modified data to the server. And when that is successful, we use our event bus to also propagate this information and any other data that's retrieved back to the presenter and then to the views. This is how we've been able to support offline interaction in our apps. I would hand over to Annyce to continue this.
Thanks, Moyen. So in order for this to work, there had to be a lot of communication between the app developers and the server team. And we really had to discuss and come to like a meeting of the minds on how we were going to implement the API. So what were some of those things we had to cover? First, we really had to think about conflict resolution. If there was some case where the app had one particular value and the server had another value, who would win? Often, we would prefer to go with what the server had stored, but then we had various corner cases where actually what the user had in their local database would win out. Second, adding timestamps to the requests. We didn't want to have to pull large amounts of data every time the person was interacting with the API. So we would add timestamps to our requests in order to only get delta updates when the person did have network access. Also, we made judicious use of status fields throughout the application. So if a user took a particular action, this could lead them to a certain state. But perhaps it hasn't synced with the network yet. They could take an opposite action and end up in a different state. So we had lots of status fields throughout our model objects in order to make sure that when things did end up syncing with the network, it was always in the correct state. Also, we decided to bundle requests. Previously, the API team would have multiple different requests. Like this example here, they may have one endpoint for showing a person's commissions, one endpoint for showing like general profile information or their roles and permissions in the app. But when interacting with the Android application, we need these things all at the same time. So we will request, hey, can you bundle these things together? Just give us one single endpoint, and then that reduces the likelihood of failure in between these various synchronous API calls. And it's because of this type of collaboration that we've really been able to find success with our current architecture. Now, it would have been extremely challenging to implement all of those things from scratch. And so, of course, we did not. We went with various third-party solutions. Therefore, I'm going to let Moyin spend some time discussing the different libraries that we chose and how we use them to achieve our end goal of always being useful to our users. Moyin?
Thanks, Annyce. Right. In our application, in order to achieve our tenants, we used 3 major libraries. We used Realm for the database, we used Event Bus for the state changes, and then we used Android jobs for scheduling jobs. I'm going to review each one briefly and then provide some highlights of our implementation. So recall that one of our tenants was to store data locally, and that's why we chose Realm. Realm was very easy to set up. It executed queries very quickly, and it had a simple API for storing and retrieving data. So let's take a look at an example of a Realm model class. Let's say we want to represent that place where the yellow arrow is pointing to on a map. So the place would have an ID and a location. We would start by declaring a class place with the Realm class annotation, and then we would implement the Realm model. Then we would define our fields as usual. So we would have the local ID field that has the primary key annotation because we want that to be unique. We have our index, that's the remote ID, and this would only be available if the place has been synced with the server. And this allows for faster lookups against those values. So this is what our database would look like if we were to visualize it. Every place has a local ID, and the remote ID is only available if the request has been synced with the server. Then we would have like a place repository class which implements repository. In this we override the add method, and then we pass in a place as a parameter. And then we have like a small ceremony to execute transactions on the Realm instance. And we copy our objects we execute a transaction on the Realm instance, and then we copy our objects to that Realm instance. And after this process, our place has been inserted into the database, and we close Realm. Now we want to retrieve our records. How did we do that? The Realm instance has like a builder-like interface, and the first method to call there is the where method, and this takes in a place class as a parameter. And then we'll specify the query requirements. So in this case, we want to retrieve a place with a specific place ID. And finally, we want the first matching response. For those of us familiar with Ruby on Rails or Hibernate, where this simple querying method should be very familiar to us. Thus, by incorporating Realm in our application, we already have a simple way to store data locally, which achieves our first tenant. And although we've been able to get up and running very quickly, it's worth stating that it did come with a few challenges, and we're constantly evaluating our options for the best implementation we can have in our app. Now, I would like Annyce to talk about how we separate UI and network requests.
Thanks. So for that, we went with Event Bus. It uses a pub/sub pattern where events are basically posted and then potentially sent to various interested parties. Here is a very basic setup using Event Bus. We do use Dagger for our dependency injection. And so we just want to make sure that when we're in debug mode, that we get messages, but we also don't want to ever have any exceptions if there's issues with our various subscribers. So by this, just a little bit of code here, we now have an event bus available to us throughout the entire application. So if you recall from earlier, Moyin mentioned that we use the MVP pattern. So this is an example of a particular presenter that would have a bus injected into it, as you can see here. The next thing we would do is register with this bus whenever the view is attached. And then, of course, when we detach the view, we would also unregister with the bus. So flashback to when we saw this example of how the different components were interacting with each other. Whenever the user takes an action, the bus is the one that's responsible for propagating that event back up to the presenter from any background jobs. In practice, this will look like the following. So say we're going to execute a queued request, and this is using retrofit. Then we would check to see, hey, is this response successful? If so, we would post an event to the bus with the updated information. Now we're back here in the presenter. It subscribes, It subscribes to that particular event, and then it takes whatever action it needs. So maybe it's going to display a message to the user, or maybe it's going to change the UI in some way. But this way, the presenter only subscribes to information that it cares about. We've also been able to take advantage of what EventBus has as far as priority of events in order to show notifications to our user. So the key thing to keep in mind is that most of the time, the person will have already been somewhere else by the time their data syncs with our network. So we want to let them know, hey, the payment actually was successful, it went through. So we use this in order to show them notifications. And we have a service that we run as soon as the application starts, and it subscribes to various events that we care about with a priority of 1. The default priority for all events on EventBus is 0, which means that if the application is running, it can suspend the events and the person will never see a notification. Otherwise, we will fall into this code, create a notification for them, and then this gives them the opportunity to interact with us again, come back in the application, and see what changed now that things have synced with the network. EventBus has really helped us out a lot in having this really straightforward interaction between the different components inside of our application, and it really supports our goals of separating the UI and the network. We've also started to use a lot more of RxJava when it comes to complex interactions between different UI components, and that's also been extremely beneficial in giving our users the kind of understanding that we're always reactive and we're never blocking them and they can always keep moving forward. Our final tenet is to queue requests whenever needed. This is very critical for us because, as we mentioned, they're often working without any network connectivity at all, and we don't want them to lose any of the data. It's also becoming more and more critical for all of you because with Android O, there have been increased limitations on what can take place inside of your applications running in the background. So to learn how we were able to deal with this inside of our application, I'm going to give it back over to Moyin.
Thanks, Annyce. All right. Like I mentioned earlier, to queue our request, we use the Android Job Library by Evernote. And what we really like about this is that it serves as a wrapper for the Alarm Manager, the Job Scheduler, and the GCM Network Manager. And in this way, we didn't have to clutter our applications with version checks to know whether our app was running on Android L or versions below Android L. And this was very efficient, and it allowed us to do background work in the most efficient manner. So I'm sure a lot of us have questions about how this compares to the job scheduler and the Firebase job dispatcher. So for us, we use, so this is how it will look if we were to compare it. And for us, we chose the Android job because we use a lot of non-standard Android devices, and we wanted to have as much flexibility as we could because the others require the Google Play Services library. So I think it just depends on what your company needs. Your options depend on what your company needs. So Android Job works by using a job manager class that has a job creator, and the job creator knows how to create various job instances of the registered job types. When a request comes in for a new job, the job creator chooses the correct provider, and thus the job is created to perform that action. Now let's look at some code. Yeah, so we have a job creator class and we have a map of all the available jobs. We also have a create method that takes in the job tag as input. And then in our create method, we look up the job provider based on the job tag, and then we create an instance of that job. So this gets us to the point where we have our desired job. In the job class, we have the onRun job method. This gets called whenever a job is executed, and this should hold the main logic for all the actions we want to happen when the job is executed. Here we would get any data that was passed to the job when it was scheduled. Here, since we stored our place in the database, we are getting the place ID that we want to sync with the server. Then we attempt to submit a request, and we can either get back a success or a failure, and then you would perform actions based on what the result was. Now, if you recall, all of this happens once we receive a request. Let's see what happens. Let's see how that request is created. In each job class, we have like a static method that defines parameters for each request. This is stored in a persistable bundle compat, and this is done so that our data will be available even after our application restarts. Then we use a job request builder, and we pass in the associated job tag so that it knows what job to run. And then here we specify any requirements for running our job. Typically, we have like an execution window in milliseconds, and then we also specify the network type we want. When making an API request, we obviously want to have an active connection. We can also check that we are not on a metered connection, or we can check if the device is charging. And I think this solves the problem that all the restricted background operations on Android O present. So we specify all the requirements here instead of having broadcasts to listen for them. Then we pass in our bundle extras, and this would include things like the primary key of the item we want to have synced from the server, from the database rather. And then we will specify that we want all our requirements to be enforced before the job is scheduled, and then we build the request. So for every request that we want to send to the network, we have some logic that determines what behavior we will use. If the device has a network connection, then we submit everything. We'll submit the request normally. If not, we'll queue the request for later using the job request setup that we mentioned previously. So lastly, we schedule the job with the job manager, and we pass in our requests, and this is how it gets added to the queue. We wait for all the requirements to be met, and we are confident that our job will be executed. This allows our users to work without worrying about whether or not they're going to lose data, or whether or not some requests will get lost because they didn't have internet connection. And then we pass in our requests, and it gets added to the queue. Oh, did I go back? Okay, so our users keep working without worrying that they are going to lose data or internet connection. And I'll pass the mic back to Annyce to wrap up.
Okay. Thanks, Moyin. So we spent some time looking at Realm, Event Bus, and the Android job libraries, the combination of which has really allowed us to have an extremely well-tested, decoupled application that works well offline. But that's not the end of the road for us. We're actually looking at even more solutions that can increase the productivity of our users. So the first thing is something that we're kind of code naming SMS fallback. As you recall earlier from that graphic, there's very little 3G connection in those areas, but there is actually a lot of 2G connection in most areas. So we want to see if we can rely on text messages in order to send notifications to the server on behalf of our users. So that's one thing we're looking at. Also, we have a lot of Kotlin in our code base now, so we want to see if we can take advantage of coroutines in order to do a few more things asynchronously down the road. And then finally, we've been working on adding push notifications to our app in order to let our users kind of always be aware of what's going on, as well as to get changes immediately that particular user may be interested in. So we're very extremely just happy with what we have, but we know that we can do better, and we're excited for what lies ahead. Thank you so much for attending our talk. We do have time for questions, but this is where you can reach both of us. And if you go on our Twitter pages, you should be. So yes, thanks again.